Hi there, folks. Hope you're all doing well. Hope you've been enjoying reading week and studying, not just fooling around. I mean, I'm at home fooling around, not while I'm recording this. I'm actually recording this pre-reading week. But I thought I'd go through another 1600 quiz from 2010. Introduce some more questions. These will be matrix-style questions. I've looked ahead and seen the quiz. It'll be from Section 5 this time, giving Section 4 a bit of a snub. Now, as usual, my disclaimer is, we're going to go through this. You might see something that will appear on the test. It's entirely possible that I'm not going to go through something that's always going to be on your upcoming midterm. It is up to you to make sure you have studied everything presented in class and in the chapters of the textbook. This is more of me talking through solutions, and so if you're having trouble starting questions, having trouble thinking through questions, especially theory-based ones, this is your resource. Because we only have so much time in class. And, we can do example after example after example, but if you just memorize examples, you might not be prepared for the particular questions being asked on the midterm. But if you learn to think through a problem like a mathematician, if you learn, this is when we start making connections to theories, these are the words we start looking for, then you can begin to adapt and answer new, more difficult questions, especially theory-based ones. Anyways, let's get into it. So, question number 1, there's I think 3 questions on this. Yeah, 3. Looks a little longer, still for some reason worth 10 marks. But what have we got here? In 1, we've got a 3x3 matrix A, and we are being asked to use elementary row operations to find the inverse of A. Okay, so until we hit chapter 4 with things like the adjoint, this is going to be your basic finding inverse method. And that is, you sort of make a super augmented matrix, as I've called it in the past. Okay. Oops, I forgot the other half of it. So you augment, you add A, and you also put the same size identity. And all we're going to do is we're going to do row operations. We're just going to do the same row operation to both sides. And what's going to happen is, if this is invertible, and they're telling me to find the inverse, they're not asking is there an inverse. So I should expect to have the identity on the left side at the end of all of this. And then what's going to be on the right side is A inverse. Okay? But this is a great check if they actually tell me find the inverse, not is A invertible, then by saying find the inverse, they're sort of implicitly saying, by the way, there is an inverse. And that means I can do a little check. If I row reduce, do 8 steps of row reduction, and I get a row reduced echelon form on the left that isn't the identity, I know for a fact I need to go back and check my work. I've done something wrong. Never, ever leave it like that and say, oops, I guess there wasn't an inverse to begin with. Okay, that's really just saying, oops, I'm lazy, I don't want to do row reductions. I know they're long. Okay, we try not to make really ridiculous ones on tests, because we know everyone's error prone. But even if you're saying, oops, I'm lazy and I don't want to go back and check for it, at least leave a note saying, like, I know I screwed up, I know this should be the inverse. Okay? Will you get a pity mark? Probably not, but better safe than sorry. Explain yourself. Let the people who are marking understand what it is that you do and do not know. Okay? That's what a test is do you know things? Not, hey, let's, just try and trick up a bunch of students because we feel like it. No. We're here to try and test what it is you do and do not know. Okay? And if we have time and I find that, a bunch of people don't know something, I'm going to go back and review it. Okay? At least for the final. Anyways, what do we want to do? Well, I've got a leading 1 here, so let's use that 1, cancel out this 3 here. So we'll do row 2 minus 3 row 1. That's how we get rid of 3's. So 1, 2, 1. We'll get 0. 7 minus 3 times 2. I screwed that up in a recent video. That'll be a 1. And this will be a 0 here. So I think the numbers here have been chosen. They look scary, especially with that 18. But I think the numbers are actually going to work out quite nicely. 9, 18, and 8 stay where they are. And now we do the same thing to this side. So minus 3, 1, 0, 0, 0, 1. Okay. All right, now let's get rid of this 9. So this is row 3 minus 9, row 1. We get 1, 2, 1, 0, 1, 0. The first 2 rows of the other side, the other augmented part. The right side will also stay the same. And then get rid of the 9 is 0. 2 times 9 is 18, so subtract that from 18, that's 0. And 1 times 9 is 9, subtract that from 8 is negative 1. Okay, we'll get negative 9 here, 0 and 1. Alright, not too bad, not too bad. I've already got a leading one here. Let's use it to get rid of this 2. So this is row 1 minus 2, row 2. And that's going to be 1, 0, 1, 0, 1, 0, 0, 0, negative 1. And we'll have negative 3, 1, 0, negative 9, 0, 1. Minus 2 times negative 3 is 6, so we'll add that on to 1, and that will be 7. And, oh gosh, what are we going to have here? 1 times negative 2 is negative 2, so we add that up here. That'll be negative 2, and we'll have a 0 here as well. Okay. Okay, let's get a leading one here. So we multiply row 3 by negative 1. How are we doing on space? Okay, we're just coming to the end, but we'll get there. 1, 0, 1, 0, 1, 0, 0, 0, 1, 7, negative 2, 0, negative 3, 1, 0, 9, 0, negative 1. Our final step, let's get rid of this one. So this is row 1 minus row 3. 1, 0, 0, 0, 1, 0, 0, 0, 1. Aha, this is the identity matrix. So whatever is left over here is the inverse. It's regular 9. 9, 0, negative 1. Negative 3, 1, 0. And now 7 minus 9 is negative 2. Negative 2 minus 0 is negative 2. And 0 minus negative 1 is 1. Okay, so A inverse is negative 2, 1, negative 3, 1, 0, 9, 0, 1. Now this is the point where I'd usually say, okay, check your work, because you should be able to multiply A inverse by A. It's going to be a lot of work to multiply a 3 by 3, so you might just want to, do 1 or 2 random spot checks. I'm most nervous as to when I added this step here. Okay, so negative 2, negative 2, 1, negative 3, 1, 0, 9, 0, negative 1. So I might say, okay, is the middle row, second column, does that really give me a 1? So we do second row and second column, so 3 times negative 2 plus 7 times 1 plus 3 times 0. And yeah, that's negative 6 plus 7, so that really is a 1. I might do another random check, maybe involving this first row here, or parts of it, so maybe specifically the negative 2. So I might say, okay, do I really get a 0 down here? Okay, is that... So that would be third row, first column. So that'll be negative 2 times 9, minus 3 times 18. Boy, do I know how to pick them. Plus 8 times 9. Well, 18 is 6 times 3. It's 2 times 9, so negative 2 times 9 minus 3 times 2 times 9 plus 8 times 9. I'll take out a factor of 9 and say negative 3 minus 6 plus 8, and that's going to be 0. 0 times 9. Okay, so I did my little random spot check. I could do the whole thing, but I'm actually more confident now that I really do have the inverse. And this is sort of a time-saving technique. Just randomly pick a couple. Don't have to multiply the full thing out. Of course, if you're confident in your work, go with it. Go with the inverse you got there. Okay, so here we go. Consider two matrices, 0, negative 2, and 1, 0, and B, 1, negative 2, 3, 0, negative 1, 4. Figure out the product AB. Okay, Well, we've got these already lined up, so I might say something like 0. So first row dotted with first column, so that's 0 times 1 is 0, plus negative 2 times 0 is 0. Okay. Then we do first row dotted with second column, so 0 times negative 2, 0 times negative 2, plus negative 2 times negative 1, and that'll be, not negative, it'll be just 2. And then we dot it with the third row, so 0 times 3 plus negative 2 times 4, that'll be negative 8. And now we clear things. This is why pencil is great. Can't scratch this stuff out. If you were to draw on your matrices in pen and then try and white it out, you're going to lose the question. Always use pencil on a math test. 1 and 0, so we do 1 dotted with 1 plus 0 times 0, so that's going to be a 1. Then we do 1 times negative 2 plus 0 times negative 1. Then 1 times 3. That's 3 plus 0 times 4 is 3. Okay, I've got the product. Fantastic. And now how about the product of A transpose times B? Well, we have to remember, what does the transpose do? We imagine a line along the main diagonal. Okay, the 1, 1, the 2, 2, the 3, 3 entry. And we remember that transpose just flips things back and forth. Of course, this 0, he's on the dotted line, so he stays where he is, but the negative 2 and the 1 swap places. And the other 0, he's also on the main diagonal. He doesn't flip at all. And that's all the transpose does. It changes rows into columns, columns into rows. But I transpose it really quick, and I'm showing my work as well, in case I screw up while transposing. Okay. And then we just do a matrix multiplication. You might be fast at this, you might be slow at it, that's okay. I'll go a little faster. We get a 0 up here, then we'll get a negative 1, then we'll get a 4, and then negative 2 times 1 is negative 2 plus 0 times 0. And we'll get a 4 here, and we'll get a negative 6 here. Okay. If you actually compare these, what actually happened in A? Well, this 0, negative 2, only the negative 2 and its interactions with the bottom row are going to help us when we make this first row here. And it turns out that A times B, the first row, is just negative 2 times the bottom row here. Similarly, this 1 in its position will make the bottom row here just 1 times the top row. And having flipped them around, you can see the same sort of things happening down here. This is an effect that's more pronounced when you get the scalar matrices. Remember, we defined those at one point. Scalar matrices just have the same number along the main diagonal. Well, their end result is I'm going to multiply the first row by 3, the second row by 3, the third row by 3. What we're seeing here is actually sort of what's called a permutation matrix. Sort of a permutation matrix and a little bit of a scalar matrix combined. The fact that these two numbers are swapped around, they're not on the main diagonal, means that we're actually going to end up swapping the rows. So we do negative 2 times the first row, but it ends up in the second row here. And 1 times the second row gets moved to the first row. It's actually kind of nifty, and there's a lot deeper math going on here. But we don't have to deal with permutation matrices or anything like that. But just know, for example, if we had a nice little shortcut matrix like 3, 3, 0, 0, do I really have to do all that dot product stuff? Well, no. That's the nice thing about scalar matrices. We haven't really gotten a chance to see this a whole lot so far, but it will become more important when we start talking about, say, eigenvalues and eigenvectors. But this will just end up being 3 times the first row, and then 3 times the second row. So I can just say 3, negative 6, 9, 0, negative 3, 12. Don't believe me? Check it out for yourself. Okay? That's the beauty of scalar matrices. Now I'm going to erase this now because it has nothing to do with the question itself. But I like to wax philosophical when I'm, doing some math problems and there isn't actually an exam time constraint on me. But let's move on to question number 3. State whether the following are true or false. So this is more of our true or false theory stuff. This is sort of the thought experiments from class that we don't really get to explore a whole lot. Some people, and I'm very proud of them, have come to office hours saying, I think I found a 3x3 matrix that when I square it isn't the 0 matrix, but when I cube it, it is. Doing my thought experiments, that's good. That shows that you're understanding the theory, that you're actually imagining, you're synthesizing new things, and that's sort of the highest level of any understanding of any discipline, is when you can take the smaller, the more base blocks, and combine it to answer questions that no one's ever really thought of, okay? Or things that no one's ever bothered to put down as a theorem. Okay? That's synthesis, and that is really the goal of education. Forgive me for, going on and on about that, but I do occasionally take classes to try and be a better teacher, and they're all about synthesis and analysis, and Bloom's taxonomy of understanding is a very interesting, very, very interesting thing. Okay, so question 3, and what have we got here? A. So for a 3x3 matrix A, the homogeneous system AX0 has infinitely many solutions. Sorry, if it has infinitely many solutions, then A is invertible. Okay, this is sort of your very basic true-false question. It's just a rewording of a theorem that we learned. Okay, and this is why we bother to write down the theorems in class. This is why we mention them, why we give them names, so that you can look them up in the textbook. Okay, and this is I don't know which one off the top of my head it is in the textbook. There's one like this in 3.3 when we do invertible matrices, because I know 3.3 is the inverse matrices section. It's the first version of the fundamental theorem of invertible matrices. You can look it up. But it actually says that if you're invertible, then the homogeneous system is going to have exactly one solution. And if the homogeneous system has exactly one solution, then you're invertible. Okay, it's a two-way street. So this isn't making new connections question. This is, do you remember that theorem? Because you need to know that theorem here. Now, on the other hand, if I didn't remember that theorem, what could I do? What could I do? Because we always sort of want backup strategies, just in case our mind blanks. Of course, if our mind's blanking, are we going to remember our backup strategies? I don't know. But, okay, what could I do? Well, I could try and make a homogeneous system that has infinitely many solutions. If this statement is true, then the homogeneous system that I create, having infinitely many solutions, should be invertible. And it's got to be a 3x3 matrix A. So, I don't know, let's just make something that has infinitely many solutions. And you might say, well, this is insane. How could you just make something off the top of your head that has infinitely many solutions? Well, if you're someone who's a lot stronger in say, row reduction, in the chapter 2 stuff, you might be a bit more comfortable saying, okay, if I want infinitely many solutions, I need parameters. Okay, when do I get parameters? When I row reduce, and there's a column that doesn't have a leading one. That's when I get parameters. So I just need to, and it'll be homogeneous, so I won't get no solutions. This'll work out great. It doesn't have to be a fancy matrix. Here's one. Okay, it's row reduced here, which is going to help us in a moment. But it does have a column without a leading one, and that means it's going to be a free variable. In fact, we'll get x is 0, x2 is 0, and x3 can be whatever I want, because I multiply x3 by 0 here, and yeah, that equals 0. This has infinitely many solutions. Now, is this invertible? Absolutely not. Okay. Why? It's in row-reduced echelon form, and we don't have an identity. And we made that remark in question number 1 here. We knew that if you're going to find an inverse, you'll do all this row reduction, and you should get the identity matrix. So this, already being row-reduced, and not being the identity, kind of signals that this isn't invertible. Okay? So we circumvented it. We didn't have to know exactly the theory that says, no, this is false. A equals 0 has one solution exactly when A is invertible. Okay, it's a two-way street. If you're invertible, one solution. One solution, you're invertible. Okay? But we didn't have to do that. We were more comfortable with augmented matrices, maybe talking about ranks, maybe just using free variables. We can construct a situation that we are more comfortable with and say, oh, yeah, this isn't invertible. So just because there's, sort of a sledgehammer of, yeah, there's a theorem that just does this instantly, doesn't mean it's the only way to think about a problem. Okay? And that, it doesn't happen with every question, but it's a useful thing to sort of stay in your wheelhouse that, I'm sort of uncomfortable about this. It's talking about matrix operations. Can I make this a systems question? Can I make this a vector question? Can I make this a subspace question? Is there a way to do that? And so if instead of just memorizing all the theory, you learn how to turn different types of questions into ones you're more comfortable with, that's great. If you hate systems, you think, oh, that's annoying, but you like the theory of row reduction and matrix operations in elementary matrices, try and shift. Sometimes some questions you can, not all. But sometimes you're lucky and you can change the question or rephrase it or make examples that you're comfortable with. Okay? Ideally, you're good at all chapters, but you might find that, wow, I really know chapter 1 and I really know chapter 3, but gosh, I suck at chapter 2. Okay? If you find that, chapter 2 is the questions you should be focusing on. Search out every possible chapter 2 question you can get your hands on. Learn how to do it. Be ravenous about it. Okay? Never say, oh, I don't like those questions, they scare me. I'm not going to do them, I'll just hope they don't pop up. Of course they're going to pop up on the exam. Of course we're going to have an invertible matrix question. Of course we're going to talk about diagonalization on the final. Of course we're going to talk about orthogonal matrices and normal matrices and all those sort of... No, I said orthogonal matrices. I mean, there are orthogonal matrices, but I meant to say orthogonal vectors. Of course we're going to talk about these things on the midterms or on the finals. Okay? You have to be comfortable with them. Okay? And we don't get comfortable by hiding in a corner. We get comfortable by learning how to do the questions, by asking our friends, by coming to office hours, as I mention all the time. Okay? We're here to, myself, Professor Lemire, the TAs, we are here to help. Okay? Because we know this stuff, and we want you to know it too. All right, rant over. Let's get question 3b. That way we can finish this video off. All right, so another true-false. If x and y are invertible matrices of the same size, and we know x and y is also invertible, then it turns out the inverse of x and y is x inverse y inverse. Okay? This is another one where we did have a result. I think it's something like theorem 3. Actually, you know what? I don't want to start saying theorems because I think I'll screw it up. But I want to say 3.5 maybe, like theorem 3.5, something like that. But it had 5 parts to it, and it talked about things like if A is invertible, then CA is invertible, and here's how you figure out its inverse. Okay, it was that one. I think it's 3.5. I don't know. But do we remember it? And so this is a great way for us to make true or false questions and really weed out the people who don't know theory and who sort of just glanced at the book or something like that. Is we'll give you a result that's very similar to a theorem, but we'll switch the matrices, or we'll make it a square instead of a cube. Little things, okay? Or we'll make it a cross product, not a dot product. And so that's for the people who really understand the notation, really understand the meaning, really understand the theory. Okay. Now here they're saying xy is invertible. Okay, but they're proposing an idea for its inverse. So couldn't we just check? Couldn't we check? Well, I know, for example, that xy inverse times xy should be the identity matrix, whatever in you need. I'll just call them I for right now. Okay? They're proposing that this is the inverse. So then I should get x inverse, y inverse, xy, and it should be I. Well, I'd really like to cancel these two out. Now, I say I'd really like to cancel these two out. I actually can't. Okay? And this is the difference between the students who say, well, this should work out. I think this should work out, so it does work out, and I'll just write it down. And the students who took it to heart when I said, the theorems tell us what we're allowed to do, and if we don't have a theorem that tells us you can do this, or this cancels out, or this turns into this, then you don't do it. Okay? The same students who think this y inverse and this y will cancel out, and this x inverse and this x will cancel out, are the same students who say matrix A times matrix B, that's got to be the same as matrix B times matrix A. No, if you don't have a theorem, it doesn't count. It does not count. So, no, we don't just get to cancel these ones and then cancel these ones and then say, it's the identity. No. Okay? What would the inverse actually look like? And this, we sort of have to remember a little bit about how we proved it. We did prove this one in class. you need to cancel this x out, so why don't we use its inverse? And once that's gone, we'll just have y left. How do we cancel out a y? Well, we use y inverse. Okay. We also made quite a point of this in class at one point when we were talking about elementary matrices. And I even wrote this up on the board. When you do a product and you take the inverse, it's a product of the inverses, but the order reverses. Okay? We wrote that on class. Wrote that down up on the board. It was the last thing I did on one day. I think it was a Friday. Okay, inverse of a product. Incidentally, this one here is false, in case you haven't gotten the drift yet. Inverse of a product equals product of the inverses in reverse order. Okay, so x times y, the inverse should be y inverse times x inverse, not x inverse y inverse. How else could I do this? Because I'm spouting a lot of theory, and it's questions like this that make you realize, oh, gee, I should probably know the theory. Yeah, you should. Peruse the theorems. Try and make connections on your own. Come ask questions. What does this one actually mean? How should I think about this one? But more than that, if you don't know theory, if you're just a calculation nut, say, okay, can I come up with two invertible matrices, x and y, and talk about their product, and then actually do a calculation for this? Now, I'm not going to do that because it's going to take me quite a long time, but here's how I might start it off. Okay, I might start off by saying, okay, if this is true, then I should be able to pick any invertible x and any invertible y, find their product, all things that I can do if I like calculation, and then take their inverse, and it should be the same as taking the inverse of the x and the y and multiplying them together. How could I make invertible matrices? Well, unlike the previous question, where they said a 3x3 matrix, this just says invertible matrices. And we're often, especially if we're good at calculation, we're often very good at, say, dealing with 2x2 matrices. It's very easy to tell if a 2x2 is invertible. It's very easy to find the inverse. We even had a theorem that gave us a formula for that. So, okay, here's an x. And, I don't know, here's a y. How about a 2 and a 2? And we'll maybe make this a 3 and a 1. How am I doing this so fast? I've been doing linear algebra for a very long time, but let's check. I've got A, B, C, D. How do you tell if it's invertible? AD minus BC needs to not be 0. 2 times 2 is 4, minus 3 times 1, that's a 1. 0 times 0 minus 1 times 1 is negative 1. So we're good to go. We can even get the inverses of these and start multiplying things together. Now, as I say, that's a very calculation-based way to do it. I'm not going to go through all those steps. I've sort of said the theory works. I'm someone who likes the theory. But if you needed a calculation way to do it, you could do a lot worse than just saying, oh, I'll just pluck some invertible matrices out of my head. Make them not your ordinary, your average invertible matrices, certainly. Don't make it, well, the identity and the identity, because if you make your matrices too simple, sometimes quirky things can happen. But I'd say those two were sort of random enough matrices that, yeah, I don't think x times y has an inverse of x inverse times y inverse. Okay? But really, the theory was the shortcut there. If I understood the theory, if I knew the theorems from class and how they applied, this was not a problem for me. I got this question right away. False. And that's going to finish off our quiz here. So that's, I think, our third one. Thank you guys for watching. If I have more time, I will do more. But I think I'm done for a little while. So, just check the playlist every once in a while through Reading Week, and I might have it updated. Okay? Happy studying.